Perfect. So I'm very glad to be here to do this tutorial, and as mentioned, it will be focused on the simulation of multiphase gas liquid bubbly flows and boiling flows using reacting Euler foam. I want to first try to give an introduction on reacting Euler foam, and in more general on the multifluid model family, let's say, and then going on to two examples or two cases, one for a bubbly flow and the other one for a boiling flow that I have also updated on the Dropbox repository. So, okay, let's start. So all the two cases will be based on the use of reacting Euler foam, which is essentially the Eulerian multifluid solver that is implemented in OpenFOAM. And what this solver does is solving a set of conservation equation for mass, momentum, and energy for each of the phases. And a single pressure equation that is shared between all these phases. Now, the model is essentially, the solver is the reference for multifluid modeling in the OpenFOAM, and has many additional features. There are frameworks to implement mass transfer, to implement heat transfer, different species in a phase. So it can be extended to cover many phenomena in multiphase flows, such as boiling, as I will give an example later on. There were two solvers. One is reactive multiphase Euler foam for an n number of phases, which I will be using, and to reacting two-phase Euler foam, which is more or less a simplified version of reactive multiphase Euler foam, because it's implemented only for two phases. So in this case, for example, it is sufficient to solve for one equation for the volume fraction, because the other one is automatically given. This was until version 7. Now in OpenFOAM 8, the two solvers have been joined into one single solver. Okay, so a few words about multifluid modeling and what is multifluid modeling about. So if we consider, I don't know if, I hope you can see my mouse moving on the screen. If you consider gas bubbles dispersed in a liquid, such in this case, now, if you imagine to have a phase marker function, which assumes the value 1 in gas and 0 in liquid, if you fix in a point or in time, or in a point in time, and go through time, that or also if you go through in space, that function will go from 0 to 1 if there is gas or liquid present. So no other conditions are possible, because there are well-defined bubbles present. So what multifluid modeling does is take an average of this situation. So if we imagine to do an average over one of those cells, and we integrate that function that goes from 0 to 1 in that cell, what we end up with is more or less the volume that is occupied by the gas phase in that cell. Now, there are different formulation of the multifluid models derived with different methods of averaging based on time averaging, space averaging, or ensemble averaging, but the basis of the equation are the same. So what happens if we average this domain, and other than that phase marker, we average also velocity, we average also density, we essentially end up with this situation here. We don't have any more bubbles in that space, but we end up having simply some volume of gas and some volume of liquid in the same cells, each one having his own velocity. So essentially, we derive what is called the concept of interpenetrating continua. So we don't have single well-defined bubbles anymore, but we have some gas, some liquid, and each phase becomes present everywhere in the space with its own property, density and velocity. We are able to derive, as you can see here in the box, two different sets of conservation equation, mass, momentum, and energy, one for the gas and one for the liquid. And in this way, we obtain a model that is quite robust and generally applicable. With that, I mean that given that you don't need to resolve each single bubble in the field, now the model is quite easy applicable to very large, complex domain where you have a very large number of bubbles, domain that are quite difficult to simulate with CFD if you need to resolve all the single bubble shapes. But at the same time, the complexity that is introduced by doing this averaging is that we lose the interface. We don't have the interface anymore. We simply have some gas and some liquid that flows in that cell, and they don't see each other unless we close the system of equation with additional terms that needs to be modeled, of course, because we don't know any more about the surface of the bubble. So we need additional modeling to represent the interaction of the interface between these two phases and all the exchanges of mass, momentum, and energy at that interface. And of course, those terms are function of the interface shape that we don't know. So for small bubbles, the physics is different that for larger bubble, and is again different for example, a stratified flow of some gas and some liquid. So to go into a bit more details, if we focused on a system, an adiabatic system, so we don't have mass transfer, and we have only a mass and momentum balance equations, and you can see the momentum balance there. So that equation will be solved one for each phase, as I said. But what couples the two phases is these terms m, which is in the momentum equation is the sum of the forces that acts between the phase, and is needed in that model to model the interaction between those two phases. And generally, the forces that are included in those terms are a drag force, a lift force, a wall force, virtual mass, and turbulent dispersion force. So 5 forces to model the interaction between the gas bubbles and the liquid phase. And without including these forces and proper modeling of these forces, the two phases won't see each other essentially, except for the geometric constraint, so that given that there are two phases, one phase cannot occupy the entire volume there. So let's try to give an example of two of these forces of how this modeling works. So if we have a bubble here that is rising in a liquid in the vertical direction, so the bubble, because of buoyancy, will be faster than the liquid, which means that there will be a flow, a recirculation flow of the liquid around this bubble, and this exerts a force on that bubble that, if we use, for example, a volume of fluid model, we resolve in the computation. In this case, instead, we need to model that. And that is modeled with the drag force, which essentially models the resistance from the fluid to the movement of the bubbles, and enables calculating the right rising velocity of that bubble. You see in the equation for the drag force, and how that is modeled, in particular the drag coefficient is with an empirical correlation function of the bubble Reynolds number and of the Eötvös number. There are different kinds of correlation, and many are the options also available in reacting Euler form. At the same time, imagine that, okay, if there is a shear flow and not a for example, a quiescent liquid, but there is a flow also of the liquid, and you have a gradient in the liquid velocity, that means that the recirculation is not symmetric around the bubble surface. And these will generate a force that is perpendicular to the main bubble motion, and this is normally called the lift force. And we need in this model an additional submodel to model the action of this lift force that you see here, and another correlation to model the lift coefficient. One of the most used is the Tomiyama correlation for that lift force. And the things to say about this correlation and about the lift force for bubbles in general, and that this goes from positive for spherical bubble and to negative for very large bubble that are deformed, that therefore are, so small bubbles are pushed, in this case, to the right towards the direction of larger relative velocity, and larger bubble will be pushed to the left towards the region of lower relative velocity. And I will speak also about the other forces later on in the tutorial, when I will see how to activate those forces in the settings of the solver. So this was a try to give a quick overview on the basis of this kind of model. And now I will move on to the first tutorial, which is the simulation of a bubbly flow in a vertical pipe. So we have a liquid vertical flow in a pipe with velocity coming in from the inlet section. And at the inlet section, that are also bubbles that are injected in the flow. And what we want to do is being able to predict how these bubbles distributes in the pipe, and also how they affect the fluid flow. So I've used as a reference the pipe flow used in the experiment of Liu, so that we can also do a little bit of comparison against some experimental data. It was an experiment done with air bubbles in water in ambient conditions, sorry. And the pipe diameter is a bit more than 5 centimeters, and measurements were taken at 60 pipe diameter from the inlet section. So what do we know? We know the superficial velocity, which are essentially derived from the mass flow rate of the two phases. We know the volume fraction of the gas, and we also know the average bubble diameter of the bubbles. Now, here an important things to mention. This case, and I've used this case because bubbles have what is called a monodispersed bubble distribution. Now, normally in a bubbly flow, bubbles have different size, and which means that their interaction with the fluid changes as a function of the size. If you see here drag force and lift force, in all these models, there is the bubble diameter. So drag and all the forces changes going from a small bubble to a large bubble, and the bubble change their behavior. For this case, bubble have almost all the same size. That means we don't really need to characterize the full spectrum of the bubble diameter, but we can represent that population with a single constant bubble diameter. And we will see later on what this means when that's not possible for the boiling flow case. Okay, so let's start with the setting up of the case from the geometry and the mesh. The geometry and the mesh were done using block mesh. What I've done is essentially create a 1/4 section of that pipe. And to be able to do a good structure mesh, I've divided that pipe in 3 blocks. One small in the center, and two round portion on the outside. Now, the internal part is 40% of the total radius, but that's actually that's not a fixed value. It can be changed, and different configurations can be used. You see the definition of the blocks here on the left, and the mesh element used to mesh the pipe. what I plan to do now is try to switch a bit between the presentation and the file. And so if we have a look at the block mesh dict, you see the definition of the vertices there. I've put the main features on the slide, but the three blocks defined with the mesh. Oh, yeah. What I was going to say is that I've used equally spaced mesh element because I'm using a high Reynolds wall treatment, and it's fine to use equally spaced elements in this case. Of course, you have to define curved edges on the wall surface of the pipe. And the other thing to say is that the boundary definition, we have the wall, an inlet and outlet patch, and also the two lateral surfaces are defined as symmetry, and they are a symmetry boundary condition is imposed for all the variables, all the relevant variables. Now, instead for boundary and initial condition, let's go back again to the case. Of course, we have the typical structure of an OpenFOAM case with the zero folder constant system. You see the results are also there in this case. So here you have all the variables in the at the beginning of the simulation that you need to set up. We still have temperature there because the model solves also for energy. It's essentially an adiabatic case. Temperature remains constant across the simulation. So let's go back to the presentation and see the most important things to set up between boundary and initial condition. So the velocity is imposed with a fixed value at the inlet, and the velocity is calculated from the superficial velocity that we know and the volume fraction of the gas. And you see here the results of the calculation and the value of the velocity used. Those values are considered uniform on the inlet section and also uniform in the domain at the beginning of the simulation. And instead at the wall, we have a no-slip condition for the pipe, and instead a slip condition for the air. Instead, at the outlet, we imposed a zero gradient condition, but instead of imposing the normal zero gradient condition, we use this pressure inlet outlet velocity boundary condition, which essentially says that if there is outflow, there is a zero gradient condition. If there is inflow, the value of the velocity is imposed from the value in the nearest cell. And also you can set up the flux to use to evaluate if there is inflow or outflow. For the void fraction, we also used, again, a fixed value at the inlet section of the pipe, equal to 0.106, which is the value we know from experiment. Of course, we need to fix also the volume fraction of the liquid, and this will be 1 minus the volume fraction of the gas, which is named alpha in all these presentation. These values are considered uniform at the inlet and also the entire domain as an initial condition. There is a zero gradient condition at the wall. Maybe I will show the file. So we have the fixed value at the inlet. Instead, at the outlet, we use this inlet outlet boundary condition, which is the same as before for the velocity. If there is outflow, it considers that a zero gradient condition. If there is inflow from that condition, the value of the void fraction instead becomes a fixed value, which is again fixed equal to the internal field. Zero gradient at the pipe, and you see there the symmetry boundary condition that is imposed on all variables. Instead, for the pressure, we used a fixed pressure condition at the outlet, and using the PRGH pressure condition, because the solver solves for this modified value of the pressure, and this condition essentially calculates the equivalent for PRGH of a fixed pressure boundary condition. And the inlet and at the wall, we have a fixed gradient instead of a zero gradient, and that fixed gradient is imposed using the fixed flux pressure boundary condition, which means the gradient is fixed at a value that allows to respect the velocity imposed by the velocity boundary condition on the same, of course, location. Okay, and this is almost, well, not everything. There is something later on a little bit more to say, but the most important features of the boundary condition for velocity, pressure, and volume fraction. If we go back to our momentum balance equation, we have the M terms that I mentioned, but we also have an additional terms to solve, which is the turbulent, which is related to the effect of the turbulence. And so we need to couple to our model also a turbulence model. And the models, the turbulence model are declared in the constant folder. And for these models, we need to define, you see there, we have turbulence properties for water and air. So we will need to define a turbulence model for the water or the air, and different options are possible. In this case, we use a general K epsilon model for the liquid phase. So based on the eddy viscosity assumption, and we solve one equation for the turbulence kinetic energy and one equation for the turbulence dissipation rate. For the air instead, we consider a laminar flow of air, and this is normally acceptable in bubbly flows because air has a much lower density with respect to water, and so it won't have so much effect. So it's actually absolutely fine to neglect a turbulence model for the air phase. Next, let's move to the important thing is at this point, since we have defined the turbulence model, is how we, and we have a wall, which is quite important in this case, how we model the wall region and what wall treatment we use. In this case, we use a wall function approach, so a high Reynolds wall treatment. And we use the single phase wall law at the wall, and this is imposed using the boundary condition for the turbulent viscosity. And you see here at the wall, we have imposed the wall function boundary condition. And so the turbulent viscosity there is imposed to respect the law of the wall, or following the law of the wall. At the wall, we have a zero gradient condition for the turbulence kinetic energy. Instead, the turbulence dissipation rate is imposed in this first cell near the wall. And those are again done using the pipe wall boundary condition in the file for the water turbulence kinetic energy and epsilon. And as you see there, for the wall, for the K, I use a KQR wall function. Maybe now I will switch just for a moment to the files. For the turbulence kinetic energy, the zero gradient is imposed using the KQR wall function boundary condition, which is essentially for turbulence kinetic energy imposes a zero gradient condition. And instead for epsilon, we use the epsilon wall function boundary condition that fixed the value on that last cell near the wall to this value here prescribed by theory. With for inlet and initial condition on both K and turbulence dissipation rate, We use some single phase estimation to have a little bit of turbulence coming in the pipe and at the beginning of the simulation. And you see there the equations used for that calculation. And we have zero gradient condition at the outlet, again, using the inlet outlet condition. The other things to set, now we have covered more or less everything that is important in the zero folder. So initial and boundary condition. We have covered the turbulence models. Another thing we need to cover in setting up the cases, of course, the properties of the two phases, which are again specified differently from air and water, a file for each, and a thermophysical properties file for each. There's not really a lot to say. It's a case with adiabatic conditions, so we use constant properties for both air and water, and we use typical values that are valid for ambient conditions. So you see there that we have a constant density considered for both phases, and that is acceptable for this case. Now, probably the most important files there is, you see that there is these phase property files. So we have set up everything, but we have not yet talked about what I mentioned at the beginning. So all the interaction between the phases, that is really key to correctly reproduce this bubbly flow. And all these interaction and all the interfacial exchanges is handled by the phase system model, and which forces or heat transfer mechanisms to consider between the phases are declared in this phase properties file, which is located in constant. Now, the base class that handles all the interfacial interaction is the phase system class. And other than calculating the different terms, source terms for momentum interaction, energy interaction that goes in the balance equations, that also initializes and handles the single phase models for each phase. Now, there are different types of phase system implemented in this code, and these are implemented as template classes so that they can be added step by step, starting from the base class. This is because each one of these phase systems does a different things. So we have the momentum transfer phase system that implements the function needed to calculate the interfacial momentum interaction. Then we have the phase transfer phase system that does the same for mass transfer. And then we have different heat transfer phase systems that does that in different ways for the heat transfer. So the type of multi-phase system we use is declared at the beginning of the file. Let's go in the file here. Here at the beginning, first thing we declare is the type of phase system we want to use, which is basic multi-phase system in this case. What does mean? That is defined in the multi-phase systems .c file, and you see on the right its definition. So we have the momentum transfer, but also heat transfer activated, and also mass transfer activated. We don't use those in this example, but that is the most basic phase system that is available. After that, we declare the phases we want in our system, so two phases, air and water. And after that, we need to declare the main properties of these two phases. So we have a dictionary for each phase, one for air, one for water. They are declared as pure phase model. And as I mentioned, we can consider a constant diameter. So the diameter of the air is considered constant, is imposed constant with the value equal at the experimental value. And as you see there, we have to impose a value of the diameter also for the water. Why is that? Because for each case, OpenFOAM is able to handle the entire range of of volume fraction concentration. So we can go for air dispersed in water to, at much higher gas volume fraction, water dispersed in air. So if that happens, the value of the diameter considered is that imposed for water. It won't happen in this case, but I just wanted to mention this as an additional functionality of the model. And in this way, the model can take into account different flow regimes that can happen in the flow and select the right closure relation for the interfacial exchanges for each flow regime. How we do that? By specifying different model based essentially on wording. So you see on the bottom left, you have air in water means air dispersed in water. So each model defined for air in water will be active when air is dispersed in water. Water in air means instead water droplets dispersed in air, and instead air and water is in between, or can also mean two continuous gas and liquid continuous separated by a large interface. And now these are blended together by the blending dictionary, which means we define a submodel, a drag model for each of these three, and until the gas volume fraction is 0.3, from 0 to 0.3, that case is air dispersed in water. Higher than 0.7 is water dispersed in air, and in between we have a blending between the three different models. And here I've left an example also in the file. You see it's there for the drag. Again, it's not needed in this case. If you define only air and water, that will be fine enough. But I've left it there just to show it works. So for air dispersed in water, we use the Ischian-Zuber drag correlation. If the flow switches to water dispersed in air, the Schiller and Neumann correlation will be used. In between, the segregated model for large interfaces is used. And essentially, there is also how we define each submodel with a dictionary. All these interfacial models are implemented between numerous classes in the interfacial model folder, in the reacting Euler foam folder, main folder. And every interfacial model is specified as a class. So in this case, we have the drag model class, which handles the drag model. So there are many models available. You can have a look at those if you go in the interfacial models folder. In this case, we use the Ischian-Zuber correlation, which is quite frequently used for bubbly flows. And instead, for the other forces, as let's go back.
Marco, sorry for interrupting. Just
yes.
a minute. Are you sharing also the terminal or not? Because we can only see the presentation.
Oh yeah, sorry. I didn't realize that. I thought I was switching between the terminal and the.
No problem.
So how do I do that? Let me.
I think you need to. Yeah.
Can you see the terminal now?
Yes, now we can.
Oh, sorry, because I probably shared directly the presentation and not my screen.
No problem. I think most of the thing that you explained was also in your presentation. So that's
yes, that's true. I hope it was clear then. Okay, yeah. But so now you can see the drag dictionary with all the model.
Great. Sorry for interruption.
No, actually, thank you very much. I should have noticed before. And then later on, below, you see the other forces that we consider. We consider lift. And for this, I've defined only air in water because it's the only condition found in this case. For the lift, we use a constant coefficient, although again, correlation are available, such as the Tomiyama model. We use wall lubrication, which is another force that, okay, for these bubbles, lift will push the bubbles towards the wall, and the wall lubrication is a force that acts in the region, in the very near wall region, and prevents the bubble to move further towards the wall. This is implemented using the Ozokawa model, which instead is not available in OpenFOAM, but I wanted to use this because I've provided this as an additional library, and this is uploaded also in the Dropbox folder that you can use. And I wanted just to provide that as an example of how to add an additional interfacial model that is not available in the model that is released. Then we had another force add, which is turbulent dispersion, that essentially models the effect of turbulence on the bubble. Turbulence will randomly mix those bubbles, and this effect is taken into account by the turbulence dispersion force, and we select the model of Barnes. Yeah, those are essentially all the forces we consider at the interface. And let's say a few words on the numerics and on the solution controls in our system folders. So more or less, the case is standard OpenFOAM. So we have every schemes, every solution, contradict. We have the block mesh, which I had shown before, but actually I didn't. And also we have the decomposed part dictionary that is needed if you want to run this simulation in parallel. Main things to say, it's that we need to use a current number which is not too high, so the time step is adjusted to maintain a current number not higher than 0.5. And also here you see that the additional library is added to, I'll show you also in the original file. You see that the library which contains the additional wall model is added to the control dict file. For the solution, we use a pinball algorithm, and we do 3 iterations of the algorithm. And the other things I want to talk about is this phase momentum option, which is a slightly different formulation of the balance equation that provide a constant treatment of the forces at the cell faces, and is known to have some benefit to in some particular condition. Now let's have a look at some results just briefly. This is 3D image of the pipe. You see that this is the volume fraction. You have an almost constant volume fraction in the center of the pipe, then a peak at the wall, and a decrease towards the wall again, which is a common feature of these bubbly flows. You see that we don't predict perfectly well the experiment, what we predict that peak. That peak is not really evident in this experiment, but I've provided some more results here for another case. And that's the common features of bubbly flows, is that peak at the wall for bubbles that have a near spherical shape. For larger bubbles, as I mentioned, the lift for change sign, those bubbles are pushed to the center, and you end up with this void profile that peaks in the center of the pipe. And I've shown also the velocity profile compared against the experiment, the water velocity, and you see how the effect of the bubble is to really flatten that velocity profile with respect to a single phase flow. Now this case is, as I mentioned, is available in Dropbox, and I think I'm running a bit late on time, so I will immediately go to the next, which is instead a boiling flow cases. More or less the same as before, but with the addition of a boiling model. So we have heat flux at the wall, and this heat flux generates some boiling at that wall with the generation of bubbles. And this boiling is modeled using the heat flux partitioning approach. So we subdivide that heat in some contribution from single phase convection, some contribution from quenching, and some contribution from evaporation. So the heat taken away, but the production of bubbles that then detach and join the main flow. I want to focus on the evaporation, how the evaporation heat flux is modeled, because it's the main, the most important thing in this kind of model. So it is essentially modeled from the nucleation site density. So it's the number of nucleation sites on the wall that are active and generate bubble. The bubble departure diameter. So how big is the bubble when it detaches from the wall? And the bubble departure frequency, which is how frequently bubbles detach from the wall. The essential the product of those three plus the bubble volume is essentially a heat flux due to a mass flow rate of bubbles and multiplied to their enthalpy of evaporation. All the mass transfer is in the first near wall cell, and this is always to take into account that, because that makes the numerics quite challenging. And of course, for the three terms that I mentioned, we need specific sub-models. And I've put here some of the correlation that can be found in literature for departure diameter, nucleation site density, and bubble departure frequency. And these are the models that are available in OpenFOAM and that I've used in this tutorial. Also, when bubble detaches, they join the liquid and exchange heat with the liquid. So we need to model also this heat transfer. And this is done with an additional model for interfacial heat transfer that is, again, closed using an empirical correlation. An additional thing before we have considered as a constant bubble diameter. In this case, bubble detaches from the wall are very small, and then they tend to grow up in the liquid phase because of interaction with other bubble, and so mainly coalescence. So bubbles collide with each other and coalesce and becomes bigger. The other, also the opposite can happen, mainly due to turbulence. So bubble can be, a large bubble can break up and divide in two. For this large change in bubble diameter, in the flow, we need to include also a population balance model. And we use the population balance models, the class population balance models available in OpenFOAM that subdivide the bubble diameter range into discrete classes and calculates, solves an equation for each class and calculates the exchanges between the classes due to coalescence and breakup. So, and specific models for coalescence and breakup that are also included. So in this case, again, we have a boiling flow, again, a vertical pipe with a liquid flow, and this time single phase liquid at the inlet, heat flux at the wall at generation of bubble due to boiling. We model this Deborah experiment, again, which is available for the subcooled boiling or refrigerant 12 at moderate pressure. This essentially is done because at those pressures, the refrigerant has the same non-dimensional number of water at much higher pressure, in particular the pressure of pressurized water nuclear reactor. But of course, it's more convenient to run the experiment at the lower pressure. You see the data we have and the setup. Water at the inlet is subcooled, so is below saturation. And when the temperature at the wall goes higher than saturation, then boiling starts in the pipe. Settings are more or less the same as before, but now we have temperature. So we have an imposed fixed value of the temperature at the inlet equal to the experiment and the zero gradient condition at the outlet. again imposed with inlet outlet. At the wall, the imposed heat flux is fixed using this fixed multiphase heat flux condition, which essentially calculates the wall temperature that produces the imposed heat flux that we want. In one phase, the liquid phase in this case, you see on the left. On the gas phase, we use the copied fixed value boundary condition, which essentially does the same thing, but also ensures that the temperatures are consistent. Void fraction now is imposed again as a fixed value, but equal to 0 at the inlet of the pipe. As I said, wall boiling is modeled using the heat flux partitioning approach. Where it is defined, this is defined in the thermal diffusivity wall boundary condition. So in this file here, I can show that in the terminal. Okay, you see we have the definition. This boundary condition is essentially a wall function, this heat flux partitioning model that relates the wall temperature with the heat flux, and it's activated by this wall function, the alpha T wall boiling wall function, again in the thermal diffusivity boundary condition of the liquid. And you see the different parameters there. And also after it, you can recognize the models that I mentioned before. So we have to define which model we want to use for the nucleation site density, the departure diameter, and the departure frequency. And you see that the model are defined there. And those are the model that I've shown here in the as they were derived by the authors of those papers. Then thermophysical property, again, we have considered constant properties here, and some are calculated as an average between inlet and saturation, for example, the density. Of course, other than density, now we need to define the specific heat and the enthalpy of the phases because of the phase change model that is now active. We use now, let's talk about the differences that there are in the phase property file, again, where we define all our interfacial interaction. We use the thermal phase change population balance multiphase system, quite complex. It is defined here on the right. You see all the different phase systems that are used and active. And with respect to the previous one, those also has capabilities to handle heat transfer and phase change, and also a population balance model. And you see that, again, after defining the phase system, we define the two phases. We say that phase change is on, and we also initialize our population balance. In addition to the model we have before, we have to define a model also for the saturation temperature. Different model can be used, can be imposed as a function of pressure. In this case, we have used a constant value of saturation at the reference pressure, because essentially the change in pressure along the pipe is not that much, so won't influence that much the value of the saturation temperature. We also have to define the model for interfacial heat transfer, and you see that the Ranson-Marshall correlation is declared there. For the population balance, I'll switch to the terminal. It's a bit more easier. Now, before we use the constant value, now we activate a population balance. You see here population balance bubbles. And that you see here that is defined for the gas phase. So the population balance, of course, is for the gas phase. And you see that what we need to do is define size groups, which means that the bubble diameter range is subdivided into those classes, and those are the boundaries of the diameter between the different classes. And the other thing that is needed is this, and this is population, but in the population balance coefficient dictionary instead, we define the submodels that we want to be active. So you see here that we have the coalescence model active using the Prince-Blanche model, and the breakup model is active using the Luo and Svensson model. And then we have other models active due to boiling. And instead, in the solvers, more or less the settings are not that much different from before. The things to say is that this model runs at very low current number. You see that here the maximum current number allowed is 0.05, which is quite low. This is because all the mass transfer related to boiling happens in the first near wall cell, and that really makes the numerics quite challenging. Again, pimple loop is used with 3 correctors, with 3 cycles. And you see that the relaxation factors also are quite low, in particular for the mass transfer, which is this one. And what happened? And also the energy. And those are almost always needed when you're doing a boiling flow. Some results, as I did before, you see the volume fraction here that starts from 0 at the bottom, and then starts to boil here after half pipe, and there is a significant boiling near the wall. You see the comparison against the experiment of the volume fraction, quite good, not perfect, a bit too much void generated, but still good. You see the wall temperature, the liquid temperature across the radius here, that goes from below saturation, 356 in the center, so the liquid is still subcooled, to oversaturation, so boiling happening near the wall. And you see here also radial profile of the average bubble diameter. You see how bubbles are small at the wall and then increase in size because of coalescence in the center of the pipe. So I think, yeah, I think I'm just on time. A bit too long, probably. Sorry if I will cut short the question. As I mentioned, the cases are uploaded in the Dropbox folder. One thing I want to say is they probably will take a bit longer to run that normal tutorial cases, but those settings, those features or those settings of the model can be used also to model different cases that are not a pipe, so that they can be used also for example, for bubble column. Similar settings can be used, and they can, so therefore you can use those settings as a starting point for the other cases that you might be interested in. And thank you very much.